Welcome back to MathXplore Infinity. I'm excited to dive into another fascinating topic today, and if you are new here, I strongly encourage you to check out our previous video on integration and measure theory, as it laid the groundwork for what we are about to explore. So the star of the show today are LP spaces, and you might be wondering why LP spaces actually. Well, because LP spaces are like, I would say, the Swiss Army knife of mathematics. They are versatile and show up almost everywhere, from quantum mechanics to data analysis. So LP spaces actually provide us with, a robust framework to understand various aspects in mathematics. For instance, in the real world, LP spaces have applications in signal processing, image reconstruction, and much more. So, they are not just theoretical, right? But, you should actually see LP spaces as tools that actually help us to make sense of I would say, the dynamic world around us. So, before we start, let me draw your attention once again, on the fact that it's actually crucial to have a solid understanding of integration and measure theory. So if you haven't watched my previous video, now is actually the perfect time to catch up, right? It's like having the right tools in your toolbox, right, before you tackle a big project. So please stick around, right? Possibly grab a notebook and let's study the reflexivity, separability, and dual spaces of LP together. Maybe, who knows, right? Maybe by the end of my video, you might become so reflexively prepared that even LP itself will want to be friends with you. So, we will consider separately 3 cases. Okay, so we will consider separately the following the 3 cases. Namely, the first one would be P strictly between 1 and infinity. The second case would be, we study the case where P equals 1. And finally, we study the case where P equals plus infinity. Okay, good. So we start with, I would say, the most favorable one, the study of LP for P between 1 and plus infinity. Oops. So study of LP of omega, right, for P strictly greater than 1 and P finite. Okay, so well, before we start everything, so let me just write something straightforward. LP, for P strictly greater than 1 and strictly less than infinity, LP is actually reflexive, separable, and the dual of LP, right, is LP prime, where P prime is actually the conjugate exponent of P. Okay, so this is what you have to keep in mind first, right, up front. We will prove that later on, right? So we start with our first theorem. So theorem 4.10. So LP is reflexive for any P between 1 and plus infinity. So proof the proof actually consists of 3 steps. So I mean the main idea of the proof is actually to show that LP spaces are uniformly convex, right? And then via the Min-Man-Peaches theorem conclude that LP spaces are reflexive. So the proof consists of 3 steps. Right, so in the first step we first show Clarkson first inequality, right? Which is actually very useful in proving that LP spaces are uniformly convex. So you prove it first. So this is Clarkson first inequality. Good. So the statement is the following. So let P between 2 and plus infinity, right? We claim that, we don't claim, it's actually the Clarkson first inequality. So we claim that, let's call it 8, right? We probably refer to that later on. So we claim that the norm of f plus g, right, divided by 2, the LP norm of that to the power p, right, plus the norm of f minus g divided by 2 to the power p, the LP norm again. So this is less or equal than 1 over 2 times the norm of f to the p plus, let me write it here. Oh no, let me probably shift it a bit. Oh, good. So this plus the norm of, okay, good. So this holds for every f and g in LP. So note that here P is actually between 2 and plus infinity. So proof of 8 so the proof for the proof, it is clear that clearly it is enough to show that the absolute value of a plus b over 2 to the power p, right, plus the absolute value of a minus b over 2 to the power p is less or equal than 1 over 2 a to the power p, no absolute value, right, plus absolute value of b to the power p, right, and this for every a and b into R. So it's enough to show this actually. Okay, so observe first that where will I write it? That alpha to the power p plus beta to the power p, right, is less or equal than alpha squared plus beta squared to the power p over 2, right? And this for every alpha beta positive. In fact, to see this, in fact, so by homogeneity, right, this kind of, so by homogeneity, right, it's enough to assume that that beta equals 1, right, and observe that the function x squared plus 1 to the power p over 2 minus x to the p minus 1 is increasing, right, on 0 plus infinity. So how to see the combinatorial thing. Observe that here, if you kind of put beta to the power p in factor, then you get something like alpha over beta to the p, right, plus 1, right? It's also equal than here you will get exactly alpha d squared plus 1 to the power p over 2. So that is why it is enough. You can set beta to be 1 and then see that this map is actually increasing. So alpha to the power p plus beta to the power p is actually less or equal than alpha square plus beta square, everything raised to the power p over 2. Okay, so since that inequality holds, so by choosing alpha to be the absolute value of a plus b over 2, right, and beta to be the absolute value of a minus b over 2, so we obtain it's all about replacing, right? So this is absolute value of a plus b to the power p plus absolute value of a minus b over 2 to the p. This is less or equal than, this was a plus b over 2 squared, right, plus a minus b over 2 squared, everything raised to the power p over 2, right? But observe that this, the right hand side is equal to a squared plus b squared divided by 2, everything raised to the power p over 2. So this is actually less or equal than if you apply the convexity of the function which at x associate absolute value of x to the power p over 2, right, then you get that this is less or equal than this plus, as I said, this follows from convexity of the map which at x associate absolute value of x to the power p over 2, right? Of course, this is convex for every p greater or equal than 2. So Clarkson's first inequality is proved, right? So our second step is actually to, as I said at the beginning, right, when I was actually talking about the proof idea. So the second step is actually to prove that LP is uniformly convex. LP is uniformly convex, right? Let me write it here, and thus reflexive, right? For every p, and this is of course by Millman-Petty's theorem. Let me just highlight, and that's reflexive. Okay, so let's prove that LP is uniformly convex. So indeed, let epsilon positive, right, and let f g be LP element, right, such that the norm of f, the LP norm of f is less or equal than 1, and the LP norm of G is less or equal than 1, with norm of f minus G strictly greater than epsilon. So just for your recall, so we'll aim at proving that the midpoint, f plus g over 2, the LP norm, is actually contained into a ball of radius 1 minus delta, for some delta positive. So this is what we want to show. Okay, so it follows from step 1, or from Clarkson first inequality, that the norm of f plus g over 2, right, to the power p is actually less or equal than 1 over 2 of the norm of f raised to the power p, right, plus the norm of g to the power p minus the norm of f minus g over 2 the LP norm, of course, raised to the power p. Okay, so but this is actually less or equal. Observe that f and g are chosen to be in the closed unit wall, so their norm is actually less or equal than 1, and also the norm of f minus g is actually is chosen to be strictly greater than epsilon. So this quantity here is actually greater or equal than, let me use another color, so this is greater or equal than epsilon over 2 to the power p. So the right hand side is actually less or equal than 1 minus epsilon over 2, everything raised to the power p. So, and thus the norm of f plus g over 2, right, it's actually strictly less than 1 minus delta, right, with delta equals to 1 minus epsilon over 2 to the power p to the power 1 minus p, right, which is obviously strictly greater than 0. So therefore LP is uniformly convex, and thus reflexive, right? Just reflexive by minimum pitches theorem, right? And this for every p between 2, 1 plus infinity. So let me just highlight it's uniformly convex and minimum pitches theorem. Okay, good. So we proved already that LP is reflexive, right? But for P actually between 2 and plus infinity. So the final step we actually prove. So in step 3, so we prove that LP is reflexive. For P between 1 and 2. So again, the proof idea would be to, consist of, so maybe I should write it down. So proof idea, so you don't get lost along the way. So proof idea consists of constructing an isometry. Say T, right, from LP to a reflexive space X, right, to be determined, of course. Then T of LP, right, would be reflexive, right, as close linear subspace of a reflexive space. Right, so moreover, as the map T, right, from LP into the image space, right, as this map will be a linear surjective isometry. It will follow that LP is reflexive. Good. So this is basically the proof idea. In fact, why would that imply that LP is reflexive? Remember that if T is actually a linear surjective isometry, right, between two Banach spaces E and F, it's a linear surjective isometry between from E into F, right, then the space E is reflexive if and only if F is reflexive. Okay, so this is actually the proof idea. So proof, let first P between 1 plus infinity, right, and consider the operator, let's call it T. Consider the operator T, right, defined from LP into LP prime joule, right, which at U associate TU, right, which is again a linear bounded functional from LP prime to R, right, which at any F associate the integral over omega of UF. Okay, so well, you can actually check that this is obviously an element of, you can check that this map is actually defining a linear bounded operator on LP prime. So this means a the dual pairing between tu and f is defined to be the integral over omega of u of x f of x g mu x, right? And this for every u in LP. So now when you have the first claim, so our claim is that T is an isometry. So T is an isometry, right? So this means let's call it 9. So this means the norm of tu, right? The operator norm, right, in the dual space is equal to the norm of u, the LP norm of u, right, for every u in the LP. So let's prove this, right? Indeed, by Hölder inequality, so by Hölder inequality we have that the absolute value of the dual pairing between tu and f is equal to, just to go step by step, so this is this d mu, right? So now observe that u is actually in LP, right, and f is actually in LP prime, which is actually the conjugate exponent of p. So the product is actually in L1. You can actually apply Hölder inequality. So this is actually less or equal than the LP norm of u times the LP prime norm of f, right? So this holds for every f in LP prime. So and therefore if you take this supremum over all the f in the closed unit ball, right, so and therefore you get that the operator norm is the norm of tu L prime star, right? It's actually less or equal than the LP norm of u. So let's call this let's call it L1. Now you have to prove the order inequality, so to get an equality. So on the other hand, put say f0 of x, right, to be the absolute value of u of x to the power p minus 2. Let me rewrite it properly. So on the other hand, put, just to save some space, f0 of x equals absolute value of u of x to the power p minus 2 times u of x, right? This is if u of x is different from 0, right? Because p is actually, p could be less than 2, right? So otherwise it won't be well defined. f0 will not be well defined, so, and 0 else. Okay, so clearly the way we define f0, so we have f0 is an element of LP prime, right? So because because the integral of the absolute value of f0 to power p prime, this is equal to the integral of u to the power p minus 1 to the power of p prime. Well, something like this, right? But of course there is absolute value here, so let me just, so but 1 over p plus 1 over p prime, oops, equals 1. So this means p prime times p minus 1 is nothing less than p, right? So you get that the integral absolute value of f0 p prime is equal to the integral of absolute value of u to the power p, right, which is actually finite as u is in LP. So f0 is actually in LP prime, so this is true. So and the norm of f0, the norm of f0, the LP prime norm of f0 is equal to the norm of u, the LP norm of u to the power p minus 1, and the dual pairing between tu and f0 is equals to the norm of u to the power p. So those are just basic computation. So thus the operator norm of tu, right, in the dual space, by definition it's actually the supreme one, so this is greater or equal than the dual pairing between tu and f0, right, divided by the norm of f0 p prime. So so let me just write it here. So but this is equal to the LP norm of u exactly. So let's call this relation L2. So from L1 and L2, right, 9 follows. And so that is T is linear isometry from LP into LP prime star, right? So which implies that the image space, right, T LP, right, is a closed linear subspace of the dual space of LP prime, right? Because LP is a Banach space. So okay, so now assume that P is actually between 1 and 2. So let me just highlight that. Okay, so since LP prime, right, is reflexive, this is by step 2, right? Because if P is actually between 1 and 2, then we are sure that the conjugate exponent of P, which is P prime, is actually beyond 2. So this is by step 2. Just highlight that, and let me just write the reason why. In fact, observe that for P prime is at least greater or equal than 2 and strictly less than n plus infinity. Okay, so LP prime is reflexive, so it follows that LP prime star is also reflexive. This is by corollary, I think it was 3.21. Check that out. It was actually on reflexive spaces. So, I mean, Banach space is actually reflexive if and only if its dual space is reflexive. So since LP prime is reflexive, the dual is also reflexive, and then we conclude. So we conclude by, I think it was proposition 3.20. Right, we conclude that TLP is reflexive, right? Because we saw that, I mean, any closed linear subspace of a reflexive space is actually reflexive. So TLP is actually closed linear subspace of the dual space of LP prime, right? Which is actually reflexive. So TLP is reflexive, and as a consequence, LP is also reflexive. Oops. So this ends the proof, and yeah. So let me just take this Ravi remark. So LP is also uniformly convex, right? Even for P actually between 1 and 2. So let me just write it. So LP is also uniformly convex, right? For P is really between 1 and 2. Before you proceed, let me highlight. So this is just a consequence of Clarkson second inequality. Right, so which hold for P between 1 and 2. So the statement is the following: is that the norm of F plus the norm of F plus G over 2, the LP norm, right, but raised to the power P prime here, plus the norm of F minus G to the power 2 raised to the power P prime, same thing. So this is less or equal than 1 over 2 of the norm of F to the power P, right, plus 1 over 2 of the norm of G to the power P, the LP norm of course, everything raised to the power 1 over P minus 1. And this of course for every F and G in LP. Okay, so this inequality is a bit, it's really, I mean, it's a bit trickier to prove than Clarkson's first inequality. So our second theorem, right, is actually about the dual of, of LP. So theorem 4.11, and this is actually the Riesz Representation Theorem. Okay, so let 1 strictly less than p, strictly less than plus infinity. So we are still in this case, right? And let phi, right, be a linear bounded operator on LP. Then there exists a unique function u, right, let's call it u, in LP prime, the conjugate exponent, such that the dual pairing between phi and f is equal to the integral of u times f, right, and this for every f in LP, right. Moreover, the norm of u, the LP prime norm of u, right, is equal to the operator norm of phi. Good. So before diving into the proof, let's have a remark, right, that will kind of enhance our understanding of this theorem. So remark. So say theorem 4.11. This is actually the Riesz Representation Theorem. I mean, it's very important, right? It says that, so before we proceed, let me just highlight, it's very important. So it says that every continuous linear functional on LP, every continuous linear functional on LP, right, with, of course, in the case p between 1 and infinity, right, can be represented so to speak, concretely as an integral. Right, so the theorem also says that the mapping which at phi maps to u, right, the mapping which at phi associate u, right, which is a linear surjective isometry, which is a linear, I mean, so let me just reverse the order. Good. So which is a linear surjective isometry, right? Allow us to identify so to speak, the abstract space LP dual, right, with LP prime. So this means that, I mean, the dual of this is identified or isometrically isomorphic to LP prime. So in what follows, we will systematically make this identification. Okay, so now let's go into the proof, right? Proof of the Riesz Representation Theorem. Okay, so we consider the operator. So we consider the operator T from LP prime to the dual, right? Defined by, we write it here, so defined by the dual pairing between T, U and F is equal to this integral, right? So on this for every U in LP prime and for every F in LP. So the same argument used in the proof of, so let me write it. So the argument used in the proof of I think it was theorem 4.10, right, about the reflexivity of FP space. So this was actually step 3. Right, actually shows that that we have an isometry, right? So this is the operator norm of TU is equal to the LP prime norm of U, right, for every U in LP prime, right? So this means somehow that T is an isometry. Okay, now we claim that T is surjective. So claim T is onto. So let's prove this. Indeed, let E be the image space, right, T of LP prime, right, since E is a closed linear subspace, right, it suffices to prove that E is dense in LP, the dual of LP, right? Because E is actually closed, so the closure of E for the strong topology is still E, right? So okay, so let H, we know how, we use our famous trick, right? Let H be LP in the bijoule, right, such that let H satisfy H restricted to E equals 0. So this means the dual pairing between H and TU is equal to 0, and this for every U in LP prime. So our goal is actually to show that that H is actually, vanishes identically. So since LP is reflexive, right, so this means basically identify the bijoule with LP, right? So you have H is in LP, right? And satisfy this dual pairing, right, which is defined to be the integral of UH is equal to 0, and this for every U in LP prime. So choosing U to be the absolute value of H to the power P minus 2 times H, right? So we get from the above relation, so we get that the integral of U times H, which is is equal to the integral of absolute value of H to the power P minus 2 times H squared. So this would be absolute value of the integral of the absolute value of H to the power P, right? And this should be 0, right? So this means that the norm of H, the LP norm of H is actually 0, but because the LP norm is a norm, so this actually implies, that H is actually equals to 0. So and then we are done. Okay. So now let's take our next theorem, which is actually about identifying dense subset of LP. So theorem 4.12. So the space CC of continuous function with compact support, right, lies dense in LP of Rn, and this for every P between 1 and plus infinity, and in this time P equal 1 is even included. So before proving this theorem, so let's have some notation first. So notation, so we define the truncation operator Tn, right, defined from R to R, it's defined by Tn of R, right, is equal to R if the absolute value of R is less or equal than N, and N times R divided by absolute value of R if the absolute value of R is strictly greater than N or otherwise. Okay, so and also this is just a recall. So given a set E into omega, so we define the characteristic function. At times there is a confusion between the characteristic function and the indicator function, but so here the indicator function so we define the characteristic function chi e to be chi e of x, this is 1, right, if x is in E and 0 else. So this is basically the indicator function for some people. Okay, so let's go back to the proof. Good. First we claim that given f in LP of Rn, given f in LP of Rn, given f in LP of Rn and epsilon positive, right? So there exists a function, say g in L infinity Rn, right, and a compact set say k in Rn such that g equals 0 outside of k, right? So this basically means that the support of g is containing to k, right? So and the norm of f minus g, the LP norm, is less than epsilon. So let's prove this, right? So indeed, let chi n, right, be the characteristic function of the closed unit ball, right, centered at 0 and radius n, and let say fn, right, be defined as being chi n times GNF. So by dominated convergence theorem, we write GCT for dominated convergence theorem. So we see that the norm of fn minus f, right, the LP norm actually goes to 0, and thus we may choose g to be fn, right, with n large enough. And our compact set that we are looking for will just be the closed unit ball, right? Because in Rn, closed and bounded, it's equivalent to compact. Okay, so good. So next, let delta be positive, right? Since g is actually in L infinity, right, and has compact support, g is actually in L1 of Rn, right? So you can easily check that. So, and by theorem 4.3, we know that the space of continuous function with compact support lies dense in L1 of Rn. So this is what theorem 4.3 says, that is CC of Rn lies dense in L1 of Rn. So by theorem 4.3, we know that there exists G1, the space of continuous function with compact support in Rn, right, such that the norm of G minus G1, right, the infinity norm, no, the one norm, sorry, strictly less than delta. So we may always assume that this is that the norm, the infinity norm of G1 is always less than the infinity norm of G, right? This is always possible. Otherwise, if this is not the case, otherwise this is kind of a short proof, a short proof of why we can always choose the norm of G1 to be less than the norm of G. So otherwise we replace we can replace G1 by the truncated version of G1, right, with n equals to norm of G infinity. So this means that T norm of G infinity of G1 of x, right, this will be equal to G1 of x, right, if absolute value of G1 of x is actually less or equal than the infinity norm, and this will be the norm of G infinity times G1 of x divided by absolute value of G1 of x, right, and this otherwise. And obviously you see that the infinity norm of Tn, of the truncated version of G1 with n equals to the norm of G infinity. So this is always less or equal than the infinity norm of G. Okay, so let me just close this. Good. So finally we have the norm of G minus G1, right? This is the LP norm. So this is actually, by definition, this is the integral of, this is just a short notation again, so don't get confused. So this is equal to this, right? And let me just go step by step. So this is the integral of the absolute value of G minus G1 times the absolute value of G minus G1 to the power P minus 1. So everything raised to the power 1 over P. So now observe that this is actually in L1, right? And this is actually in L infinity. So if you apply Hölder's inequality, so you get this is less or equal than the norm of G minus G1, the norm 1, and then we still have the power 1 over P times the norm of G minus G1 norm infinity. Now you have the power P minus 1 over P. Okay, and well, now what you have to say is that oops, I think I used the wrong color. So this actually, so this, one of these actually strictly less than delta, so this we know. And so this is actually less or equal than delta to the power 1 over p, right, times the norm of g minus g1, norm infinity, right, to the power 1 minus 1 over p. Okay, so now again here, I mean, can even bound the other term, so this is also equal than delta to the power 1 over p times triangle inequality, so this is also equal to norm of g L infinity plus norm of g1 L infinity 1 to the power 1 over p. But we saw that we can always assume that this is less or equal than the norm of g infinity. So at the end what we get is that this is less or equal than delta to the power 1 over p times 2 times the norm of g to the power 1 minus 1 over p. So we have norm of f minus g1, right, the LP norm of this is less or equal than the norm of f minus triangle inequality minus gp plus the norm of g minus g1 p. So this is actually strictly less than epsilon plus delta to the 1 over p times 2 norm of g infinity to the power 1 minus 1 over p. So by choosing delta positive, right, small enough that delta to the power 1 over p times 2 norm of g infinity to the power 1 over 1 over p strictly less than epsilon, right, we conclude that the norm of f minus g1 p is actually strictly less than 2 epsilon. So, and this means that this space actually lies dense in LP. I mean, remember that this was actually an element of CC of R, right? So this is what we had to show. So okay, now let's have before talking about studying the separability of LP, so let's have a definition. So definition. So the measure space omega, right, is called separable if there exists a countable family, say En, right, of the sigma algebra A, right, such that we write it in color, such that the sigma algebra generated by the ENs, right, coincide coincide with A. Right, so this means A is actually the smallest sigma algebra containing the ENs. Okay, so example. So the measure space omega equals Rn, right, is separable. So indeed, so this is the proof. So indeed, we may choose for the family En. We may choose for En any countable family of open set such that every open set in Rn can be written as a union of the ends. So more generally, if omega is actually a separable metric space, right, and A consists of the Borel set, then the space omega is actually a separable measured space. Okay, so theorem 4.13. This is about the separability of the LP space. So assume that omega is a separable measure space. Then LP is separable for any P, right, P between 1 and plus infinity. So that omega need to be a separable measured space. So we will consider only the case omega being equal to Rn, right? So as a consequence, LP of omega, right, is also separable for any measurable set omega included into Rn. So let me highlight that. So if omega is actually equal to Rn, then LP is actually separable for any omega included into Rn. So indeed, this is because there is canonical isometry. From LP of omega into LP of Rn, right? So I mean, just need to just consider the extension by 0, right, outside of omega. So therefore LP of omega, may be identified not with, but well, with a subset. If a subset, or can be identified as a subset of LP of Rn, right? And hence, I think we saw that when we talk about separable spaces, that any subset of a separable space is actually of a separable metric space, of course, is actually separable. So, and hence LP of omega is separable. And this was actually by proposition 3.25. You can check it out. Good. So now let's have a look at the proof. So assume omega is Rn, right? So let calligraphic R, right, denote the countable family of open set in Rn, right, of the form say we call it R equals to the product, Cartesian product of the set A, K, B, K, right, K running from 1 to n, right, with let me write it here, so with AK, BK lying in the set of rational numbers. So just so the sigma algebra generated by the family R is exactly the Borel sigma algebra on Rn. Okay, so now let epsilon, right, denote the vector space over Q. Generated by the functions chi R, right, R running over the family calligraphic R. So this means epsilon consists of all finite linear combinations with rational coefficient, of course. Of functions chi r, right? So that epsilon is is countable. Good. So now our claim is that remember, we want to prove that LP is separable, so we claim that epsilon is dense in LP of Rn. Indeed, let F, right, in LP of Rn, right, and epsilon positive, right? So as the space of continuous function with compact support on Rn lie dense in LP of Rn, right, for the strong topology on Rn, so they exist. There exists, of course, this is for p between 1 and plus infinity, right? There exists some f1 in cc of Rn, right, such that, put it here, the norm of f minus f1 LP norm strictly less than epsilon. Now let R being calligraphic R might be any cube such that the support of f1 is actually contained into R. Now given say delta positive, right, it is actually easy to construct, it is easy to construct a function, say f2, right, in epsilon, right, such that the norm of f1 minus f2, the infinity norm, of course, is actually strictly less than delta, and f2 vanishes outside of R. Well, how to do that? Well, it suffices to split R into small cubes, right, where the oxidation By acceleration I mean the difference between the supremum and the infimum. Where the acceleration of f1 is actually less than delta. So in fact, if you give me, so maybe you should have a sketch. So say we have, okay, so let's say we have something like this. So this would be, for instance, a function with compact support, right? So now I can approximate this function, so by kind of function in the family epsilon, in this way somehow. So this would be kind of, the idea. So therefore, so maybe I drag this thing up. Good. So therefore we have the norm of f1 minus f2, the LP norm. By definition, this is, well, let me just write the full expression, f1 minus f2 to the power p d lambda n, right? This is the n-dimensional, the best measure, to the power 1 over p. So if you actually use this is actually less equal than the norm of f1 minus f2, the infinity norm, right? Because you can always pull it out as being element of continuous function with compact support. So this is also equal than this integral over r, right? Where r is actually the support of taking f1 is actually contained into r. So this is equal to this to the power 1 over p. So but this is exactly the norm of f1 minus f2 infinity times the n-dimensional, the best measure of the cube r, everything raised to the power 1 over p. So but this is actually strictly less than, remember, this norm was actually less than delta, so this is less than delta times the n-dimensional, the best measure of r to the power 1 over p. So we conclude that the norm of f minus f2, the LP norm, right, is actually strictly less than 2 epsilon, provided that delta positive is chosen so that delta times the n-dimensional, the best measure of the cube r raised to the power 1 over p is actually strictly less than an epsilon. So with this, we end the proof, right? So LP is actually reflexive. Okay, cool, good. You have come a long way. So now let's move to the second part. So now we study L1 of omega. So we start with a description of the dual of L1. So we start with theorem 4.14, I think so. This is the Riesz Representation Theorem, but for the case p equal 1. So, but let me rewrite again. Riesz Representation Theorem. Okay, so let phi be in the dual space of L1, right? Then there exists, I mean the statement is basically the same. There exists a unique function CU, right? CU in L infinity, right? Such that this dual pairing is equal to UF for every F in L1. So moreover, the norm of U, the infinity norm of U, is exactly the operator norm of phi. So again, the Riesz representation theorem actually has said that every continuous linear functional on L1 can be represented concretely as an integral. So, and again also, we can also identify L1, the dual of L1 with L infinity, and this is what we do. I mean, this is what we'll be doing, right? So, proof. So for the proof, let say omega n, right, be a sequence of measurable set in omega, right, such that omega can be written as the union of omega n, right, and the measure of omega n is finite for every n. I mean, this is for the simple reason that I think it was actually in the previous video we said that throughout this this lecture series we assume that omega is sigma finite. So this is due to the sigma finiteness of omega. Now put say chi n, right, to be chi of the set omega n, so the indicator function. So we first prove uniqueness of U. So uniqueness. Uniqueness of U. Good. So let V, right, be in L infinity such that this dual pairing of phi f is equal to the integral of Vf, right, for every f in L1. Then we will have that the integral of U minus V times f is equal to 0 for every f in L1. So choosing f, right, to be to be chi n times the sine of u minus v, right? So I mean with the convention that that the sine of 0 is 0, right? So we get that the integral over omega n of the absolute value of v minus f, probably put d mu, is equal to 0. So this is of course for every n, so this means that u minus v, the absolute value, is equal to 0 almost everywhere on omega n for every n. So this means that u equal v almost everywhere on omega n and for every n, and thus u equal v almost everywhere on omega. So uniqueness is done. So now let's move to existence. Okay, so first we construct the function that we call, say, theta in L2 of omega, right? Such that theta of x actually greater or equal than epsilon n, which is positive for every x in omega n. Of course, such a function theta exists, right? Exists indeed. So maybe put it, I mean indeed, we define theta to be, say, alpha 1, right, on omega 1, right, and then we define it to be alpha 2 on omega 2 minus omega 1, and so on, alpha n on omega n minus omega n minus 1, etc., etc. And we actually, I mean, we adjust the constant alpha n, right, positive, in such a way that theta is co-integrable good. So now the mapping, I mean, which at every element f of L2 associate the dual pairing between phi and theta f, right? So note that this theta f is actually, I mean, this is already defined, right? As theta is actually into L2, right? Theta is in L2 and also f is in L2, so this means that the product, I mean, theta f is actually into L1, so by Hölder's inequality. So this mapping is, I mean, it's a continuous linear functional. Continuous linear functional on L2, of omega, right? So by the Riesz Representation Theorem for p strictly greater than 1. So by theorem 4.11, that is the Riesz Representation Theorem. So there exists a unique, so there exists a function v in L2 of omega such that, I mean, this linear functional can be represented as an integral. It's the integral of vf, right, for every f in L2. Now put it in color, put u of x equals to v of x divided by theta of x, right? This for every x in omega. So clearly u is well defined. Since, I mean, theta is being, I mean, was constructed in such a way that it's actually strictly greater than 0 on omega. So, and moreover, u is measurable. And u chi n is actually in L2 of omega. Now our claim. So we claim that u is actually our candidate claim. Claim that u is the candidate we are looking for. So this is our candidate. So it means that this is equal to the integral of uf for every f in L1, and also the infinity norm of u is exactly the operator norm of phi. Okay, so since phi theta f, right, is equal to the integral of vf, right, for every f in L2, then for f equals chi n times j divided by theta, right? So this is divided, not restricted. So we get, so let's call it star 1. So we get that phi chi n g equals to the integral of u chi n g, and this for every g in L infinity. Well, of course, I mean, this is actually in L2, right? Because f is actually, I mean, it is bounded on omega, and I mean, outside of omega, f is just 0. So f is well defined. So next, we claim that we put it in column. Claim that u is actually in L infinity of omega, and the norm of u infinity is also equal than the operator norm. So we call this second property star 2. Now fix any constant C positive, right? And such that C is actually strictly greater than the operator norm of phi, and set our input A to be the set of x in omega such that the absolute value of phi of x is strictly greater than C. So now, let's verify. Oops. So let's verify that A is a null set. I want to show that the measure of A is 0. Okay, so indeed by choosing G to be chi A times the sign of U, right, in star 1, so what we get is that phi chi n chi A sine of U is equal to the integral of U times chi n chi A sine of U. So this means that the integral over A intersected with omega n, the absolute value of U, is equal to phi chi n times chi A times the sine of U. Right, so now observe that this is obviously in L1, right? So this is well defined, and also you have this is actually less or equal than C on A. So this is also by definition, phi is a linear bounded operator, so this is less or equal than the operator norm times the measure, right? The one norm of chi n times chi A times the sine of U is just the measure of the set, this A intersected with omega n. So therefore, because the left hand side is also kind of lower bounded by, so therefore it's lower bounded by C times the measure of A intersected with omega n, right, which is actually less or equal than the norm of phi, right, times the measure of A intersected with omega n. So it follows that that the measure of A intersected with omega n is equal to 0, and of course for every n. This is because C is actually assumed to be strictly greater than the operator norm. So instead of having this, we should rather have greater equal, because this is assumed to be greater than this. So if this inequality holds, then necessarily this is 0. So and this mu of A, right, which is equal to mu of A intersected with omega, so this is, which is equal to mu of A intersected with the union of omega n right, in run from 1 to infinity, and this is just less or equal than, and this of a intersected with omega n, right? But this actually is 0, so so we get that 0, which is equal to mu of a intersected with omega n, right? It's less or equal than mu of a, it's less or equal than 0. So mu of a is 0. And this means that A is a null set. It's a null set. And I mean, you also have that the norm of U infinity is actually less or equal than the operator norm L1 psi. So this means that star 2 actually holds. Okay, good. So finally, we claim that call it star 3. Put it in color. Finally, we claim that phi comma h, the dual pairing, is equal to this for every h in L1 of omega. Indeed, it suffices to choose G to be the truncation of H, right? In star 1. Remember, star 1 was actually phi comma chi n g is equal to the integral of u chi n g. This y will be in L infinity. So it suffices to choose G to be truncation of H and observe that chi n T n H actually converges to H in L1 of omega, and this is of course by dominated convergence theorem, so you can easily check that. So now in order to complete the proof, we have to show the reverse inequality. I mean, it remains to show that the norm of U infinity is equal to the operator norm. So from three, right, it follows that from star 3 follows that absolute value of phi h is also equal than the norm of U infinity times the norm of this, right, for every h in L1, and this of course implies that the operator norm is actually less or equal than the norm of U infinity. So we call this star 4. So I think it was star 2, right, together with star 4 actually implies that the norm of u coincide with the operator norm of phi. So we finally end this proof, right? Which was rather pretty lengthy, but so far so good. Okay, so remark. The space L1 of omega is never reflexive, right, except in the trivial case where omega consists of a finite number of atoms. So let me just highlight that. I mean, you have reflexivity of the L1 space if and only if omega consists of a finite number of atoms, right? Which, in which case, we write it in color. So in which case, L1 of omega, I mean, is finite dimensional. Good. So how to see that? I mean, indeed, suppose by contradiction that L1 of omega is reflexive. Right, and consider two case scenarios. Consider two cases. So the first one, number one, put it in color. For every epsilon positive, there exists omega in omega, right, measurable, with 0 strictly less than the measure of omega, which is strictly less than epsilon. So so this means, I mean, this first case means that omega has set of extremely small measures. So the second case scenario is that there exists epsilon, I mean pretty much the contraposition or the negation of the first case. So there exists epsilon such that mu of omega is strictly greater than epsilon, or is greater or equal for every measurable set omega, right, with mu of omega positive. Again, as I said, this means that omega does not have sets with arbitrarily small measures. Okay, so in case 1, there exists, because case 1 actually holds for every epsilon, so there exists a decreasing sequence call it Wn, right, of measurable set such that mu of omega n is positive for every n, of course, and the actually goes to 0 as n, right, as n actually goes to plus infinity. Well, the idea is actually, the idea is to choose first any sequence say w prime k, right, such that 0 is strictly less than mu of w prime k, which is strictly less than say 1 over 2 to the power k, and then out of that sequence construct a decreasing sequence, and then put Wn to be the union of w prime k, right, k running from n to plus infinity. Wn is obviously decreasing, and the measure of Wn actually goes to 0 as n actually goes to plus infinity. Now let chi n, right, be the indicator function of Wn, and define Un to be chi n divided by the L1 norm of chi n. Since the norm of Un, right, the L1 norm of Un equals 1, right, so this means Un is a bounded sequence. It's bounded, and that since Un is bounded and that L1 is assumed to be reflexive, we know that it follows by theorem or from theorem 3.18 that there exists, we know that every bounded sequence of a reflexive space has a weakly convergent subsequence. So there exists a subsequence, without relabeling, so there is a subsequence, we still call it U1, right? And some say U in L1, such that UN converges strictly to U. I mean, in the topology sigma L1 joule, which is cell infinity. So this means that an integral of UN phi goes to the integral of U phi for every phi in L infinity. So on the other hand, for fixed J, right? And strictly greater than J. So we have the integral of U and chi J is equal to the integral of chi N chi J divided by the norm of chi N, L1 norm, and this is exactly the integral of chi N over norm of this, and this is exactly 1. This inequality actually comes from the fact that since n is actually greater than J, and the sequence of Wn are actually decreasing, so W n is actually contained to Wj. So at the limit, as n goes to plus infinity, so we obtain that the integral of Un chi j actually, which goes to, integral of U chi j goes to 1 for every j. However, by dominated convergence theorem, so you have that, you can check the hypothesis actually, so you have that the integral of U chi j actually goes to 0 as j goes to plus infinity, and which is actually a contradiction, because up here we have, here we have convergence to 1, and here we have convergence to 0, so it doesn't make sense. So which is a contradiction. Okay. So in the first case, L1 is obviously not reflexive. So in case 2, the space, is purely atomic and consists of countable union of distant atoms, say AN, right? Of course, unless there is only a finite number of atoms. So by purely atomic, I mean that omega is kind of the union of the indeed, so why is omega purely atomic? So indeed, if they were non-atomic or continuous, but in omega it would be possible to construct measurable set, right, with arbitrarily small measures. Within those regions. So this is because, I mean, in continuous part you could have subset with, with measures that actually approach 0. But case 2 actually rules out, the possibility of having, how would I say that, infinitesimally small measurable set. So omega is effectively purely atomic, right, and consists of countable union of distant atoms. So in that case, L1 of omega, right, is isomorphic, because you now have an L1 kind of a counting measure, so it's isomorphic to small L1, right? And in order to show that L1 is not reflexive, it suffices to prove that L1, small L1 of course, is not reflexive. Okay, for that, consider the canonical basis. Consider the canonical basis. Canonical basis En, right, which is 0 everywhere except at the nth position. So assuming by contradiction that L1 is reflexive, right, since the sequence of ENs is bounded, so there exists a subsequence ENK, right, and some say X in L1 such that ENK converges weakly to X, in the weak topology sigma L1 L infinity. So this means that phi ENK, right, converges to phi X, and this for every phi in L infinity. And here, this dual pairing corresponds exactly to, the scalar product. So choosing phi to be 0 and then 1 starting at the jth position, right? We find that I mean, this is obviously an element of L infinity, right, bounded by 1. So we find that this scalar product phi jx is equal to 1 for every j. Okay, I mean, why is it equal to 1? So let me just give you a quick proof. So in fact, phi j, I mean, enk actually goes to 1, right, for every j, right? So just scalar product goes to 1. So that means we must have phi jx, because phi j enk converges to phi jx, so we must have phi jx equals to this for every j. Good. On the other hand, phi jx actually goes to 0 as j goes to plus infinity, right? And this is because x is in L1. I mean, how to see that again? Indeed, I mean, if x, right, is in L1, then by definition we know that this summation is finite, right? We know that this series converges. So if the series converges, this means that the sum of, I mean, of the tail of the series actually goes to 0. So this means this from j to plus infinity of xn, right, which is, this corresponds exactly to the scalar product between phi j and x. So this should go to 0 as j goes to plus infinity. Okay, so again you have a contradiction, because you have phi jx that goes to 0 and phi jx that is being equal to 1 for every j. So which is a contradiction. So this means that L1 is not reflexive. Then we are done. Okay, good. So with this we actually end not the lecture. Yeah, I know, I mean, this, I mean, pretty long lecture, but so with this we end the study of the L1. So now let's finish by studying L infinity, study of L infinity. Good. So we already, so let me just recall, so we already know that, I mean, this was actually by theorem 4.14, that L infinity is actually the dual of L1. Now, being the dual space of, I mean, of L1, right? So L infinity actually enjoys some nice properties. I mean, in particular, we have the following. So let's call it number 1, the closed unit ball in L infinity, right, which is can be written as the closed unit ball of in L1 joule, right? This is actually is weak star compact. This is actually a consequence of Banach-Laoglu-Bourbaki theorem, not a consequence, but even the theorem, right? So this is compact. The weak star topology sigma L infinity L1. As I said, this is by Banach-Laoglu. Bourbaki theorem. Put it in bracket. Okay, so the second property is that if omega is a measurable set measurable subset of Rn, right, and Fn is a bounded sequence in L infinity of omega, then there exists subsequence Fnk, right, and some f in L infinity of omega, of course, such that f and k converges weak starly to f, right? So this is in the weak star topology sigma N infinity L1. I mean, this is actually a consequence of let me just write it. So this is a consequence of corollary 3.13 and theorem 4.13, right? I mean, corollary 3.13 was, I mean, stated that if I have a reflexive, I mean, a separable Banach space, right, and then I have a bounded sequence in the Joule space, then there is a subsequence that converges weak starly to some f. And yeah, I think theorem 4.13 was, I mean, okay, stated that, I mean, if omega is separable, then LP is separable for every p between 1 and plus infinity, p included, of course. So So however, L infinity of omega, right, is not reflexive. It's not reflexive, right, except in the trivial case. Where say omega consists of a finite number of atoms. So otherwise, otherwise if L infinity was reflexive, right, L1 would be reflexive, right, and this is just by corollary 3.21, right. Because we know that from by corollary 3.21, we know that the dual space is reflexive, if and only if it is reflexive. So otherwise L1 would be reflexive, and we know that L1 is not reflexive. So as a consequence of that, it follows that the joule of L infinity contains L1. In fact, this is due to the fact that L infinity is actually the joule of L1. In fact, we know that L1 is contained into the bijoule, right? But the bijoule of L1 is actually the joule of L infinity. And the joule is even strictly bigger than L1. So this means strictly contained to L infinity star. Okay, so so this means that they are continuous linear functionals say phi 8 on L infinity, right, which cannot be represented as say phi f equals to uf, right, for every f in infinity, and for some u in L1. In fact, let's try to describe a concrete example of such a functional, right? So let phi 0 I define from the space of continuous functions with compact support into R might be defined by phi 0 of f, right, is equal to f0 for all f in phi of Rn. So clearly phi 0 is a linear bounded functional on the space of continuous function with compact support, right? And though with the infinity norm. So by Unveil theorem, so we may extend phi 0 into a continuous linear functional, say phi on L infinity of Rn, because let me just write it here, so note that space of continuous function with compact support on Rn is the linear subspace L infinity of Rn. So, and we have phi restricted to the space of continuous function with compact support is equal to phi 0. So now what we are trying to do is that, let's verify that there exists no function, put it in capital letter, no function u in L1 of Rn such that we call it gamma 2, such that gamma 2 hold in infinity. Okay, assume by contradiction that such a function u exists So we deduce from gamma 1. I think I probably let's call this gamma 1. So we deduce from gamma 1 and gamma 2 that the integral of uf, right, is equal to 0, right, for every f that I take into the space of continuous function with compact support on Rn minus 0. So so this means that, I mean, this is by the fundamental lemma of calculus of variation. So this is the fundamental lemma of calculus of variation, that u is equal to 0 almost everywhere on Rn minus 0, and this because the singleton 0 is actually null set, so u is even 0 almost everywhere on Rn. Which I said it because, I mean, the best measure of this is 0, so this means this is an null set, of course, for the best measure. So we conclude if the mean of gamma 2, conclude that phi f equal to 0 for every f near the infinity of Rn. So this means that phi is actually the 0 of the dual of an infinity, but this is actually, this is a contradiction to gamma 1, which contradicts gamma 1. It's actually a contradiction to the fact that, phi is actually the extension of phi 0. Okay, well, if you feel like, the conclusion is, it's quite fuzzy, so, in fact, let me just put the comment, in fact, gamma 1 is equivalent to say that phi f is equal to f0, right? But this actually for every f in CC of Rn. So since phi is actually 0, then you get that phi of 0 is equal to 0 for every continuous function with compact support on Rn. But this is actually this is absolute, right? As one can always construct a function function f with compact support such that f of 0 is different from 0. I mean, for instance, if you actually if you're in the plane, we can have something like this. So we can have something like this, like this function, for instance, has compact support, but I mean, does not vanish at 0. Okay, so remark. Just write remark. L infinity omega, I mean, it's not separable, right, except when omega consists of a finite number of atoms. Right, in which case, actually, I mean, in this case, I mean, when omega consists of a finite number of atoms, I mean, omega is a finite measure space. In that case, it's a finite measure space, and one can construct, I mean, a countable dense subset by considering linear combination of indicator function functions of individual atoms. So, okay, in order to prove that L infinity is not separable, it is actually convenient to use the following lemma. So lemma 4.2, I don't know, something like that. So let E be a Banach trace. Assume that there exists a family, say OI, I in capital I, such that number 1, for every I in I, OI is a non-empty open subset of E. So number 2, the OIs are pairwise disjoint, so the intersection of this is empty if I is actually different from J, And finally, number 3, put it here, capital I's, the index set is actually uncountable. So in this case, E is not separable. So proof. So suppose by contradiction, that E is separable. So let then UN denote a dense countable set in E. So because the OIs are actually open, so for each I in I, the set OI intersected with the UNs means non-empty, and you may choose say NI, right, such that UNI is an element of OI. Now observe that the mapping which at I associate NI is injective. Right, indeed, I mean this is a proof. Indeed, if Ni equals Nj, then UNI is equal to U. We write it probably no, then UNI, which is equal to U Nj, is in OI intersected with OJ. And because I mean the OI are pairwise disjoint, so this implies that I is necessarily equal to J. So because this mapping is injective, so we have that the index set I is contained into N, right? And consequently I is countable, which is a contradiction to assumption 3. Good. Now we establish, I mean that so now we establish that L infinity of omega is not separable. Okay, so we claim that there is an uncountable family, say Wi, I in I, height of measurable set in omega, which are I mean all distant so that means the symmetric difference is actually has a positive measure. Of I different from J. So we then conclude by applying lemma 4.2 to the family Wi. To the family, say, define a new family, OI, right? I in I, defined by taking OI is equal to function L infinity of omega, such that the norm of F minus chi W I, the infinity norm, strictly less than 1 over 2. Just drag it, it will not fit. Strictly less than 1 over 2. Of course, you can actually check that. OI is actually non-empty, right? Family of OIs are pairwise disjoint, and I is obviously uncountable. So the main deal actually, is about the existence, right? The existence of the uncountable family Wi. So the existence of an uncountable family Wi, right, is actually clear when when omega is an open set in Rn. Just cyanide. Right, since we may consider all the balls bx0, right, with exo in omega and a positive small small enough. Okay, good. So when omega is a general major space, when omega is a general major space, I mean we split omega into its atomic part, say into its atomic part omega A, and its non-atomic part that we call omega G. So let me just do atomic part omega A and the non-atomic part. So we split the argument. Actually, I mean, we distinguish two cases, right? The first case is that the non-atomic part is not a null set. And the second part is that omega G is a null set. Okay, so in the first case, right, in case 1, so let me just highlight that. In case 1, then I mean if omega G, the non-atomic part, is not a null set, then for each real numbers, for each real number T, right, T positive and strictly less than the measure of the non-atomic part, there exists a measurable set, say omega, with the measure of omega being equal to T. So in this way you obtain, I mean, you obtain an uncountable family of distant measurable set, say WT, right, T running over R. So good. So in case number 2, right, if the non-atomic part is actually a null set, then omega consists of countable union of distant atoms. I mean, omega is purely atomic. Say AN, right? Of course, unless omega consists of a finite number of atoms. number of atoms. Okay, good. So for any collection of integers, say for any collection of integers, let's call it A, right? We define WA to be the union of the AN, right, over N running into A. So clearly WA, right, is an uncountable family of distant measurable set. So with this we end the proof of L infinity is not separable. So I think we really come a long way, right? So this is, I mean, already almost 3 hours. That is really too much. So let's summarize the main properties of the LP spaces, right? When omega is actually a measurable subset of Rn. So let's just have a so this is a summary. So but here do this and good. I hope. Okay, so here reflexive separability, and here we have dual spaces. So here we have LP, right, with I think I should change the color. So let me use probably this color maybe. So this is LP, right, with P strictly between 1 and plus infinity. Here we have L1 space, and here we have N infinity space. Okay, so just try to make it nice. LP for P between 1 and plus infinity is reflexive, so this is yes, and the dual space is actually LP prime, where P prime is actually the conjugate exponent. So for the second one, so L1 is not reflexive, of course it is separable, and the dual space is L infinity. And finally, L infinity is not separable, it's not reflexive, not separable, and the dual space is, is strictly bigger than than L1. So good. This is actually the end of the video. Thank you for watching, and we see again each other in the next video.